Thank you. We're very excited to do this webinar on this topic of EMC. And as always, please ask a ton of questions since we have an EMC expert with us today, Ignacio, to address those questions, take advantage of this opportunity. So that's my 2 cents. With that, we can get started. Yeah, absolutely. With that, we'll get started. If you don't know who CR Circuits is, we're a Silicon Valley, Bay Area PCB and assembly manufacturer. So we have good technical capabilities to build all types of boards, as well as building standard boards on a quick cycle time. That's like who we are. And we've been doing that for quite some time now. And so this is the TOC for today. And we'll definitely talk about materials, material selections, and some, pointers on design as well. And we'll end with a quick checklist for EMC and DFM. So first, let's discuss the materials. You want materials with very consistent decay and dielectric thicknesses. So when these properties vary, they can cause impedance mismatches across the board. So that's something that you want to take into consideration. It's very important. You also want to look at the thermal expansion of the material, or the CTE. And having a high CTE can definitely cause issues both with the reliability of the board as well as the performance of the board. So you have to be very careful with the CTEs. In terms of dissipation factor, or DF, materials with a high DF tend to lose more energy as heat during signal transmission, which is not only introduces insertion loss, but also increases the EM radiation. And finally, another consideration when you're choosing a material is moisture absorption. High moisture content in the PCB can alter the electrical properties such as loss tangent, electrical conductivity, insulation resistance, and it can basically result into shorts. So from a fabricator standpoint, prior to shipping, the PCB manufacturer should bake the boards to make sure there's no moisture within the boards, especially important for rigid plex. And you might want to consider packaging in a vacuum type of a situation and using a little bit more expensive packaging and to make sure that there's no moisture issue over time. So in terms of picking the materials, here are some examples. There's plenty of different material options. We have a material selector on our website. We won't demo that today. We have other tools to demo, but you can always pick materials that with a DK of less than 4. And here's some examples: FR408HR, which is popular in the automotive space, iSpeed, Tachyon. These are all good choices to help minimize the signal loss and maintain impedance consistency. And for materials with a DF of less than 0.005, you have options as listed below, Rogers and Megtron. Megtron is easier to build HDI boards with, or laser drilled microvias with sequential lamination, whereas a Rogers is less conducive to that type of a stack up. So there are trade-offs, not just from electrical properties, but from the manufacturability of the materials. And when we talk about hybrid stack ups, that's really important. Understanding what your via stacks are, of course, plays a role in how you build it, and what material you've picked will either make it more challenging for the fabricator or easier for the fabricator. So all very important. So when you're building a reliable stack up, there are things that you can do for manufacturability as well as electrical performance. And so here we've listed some of the things. So one thing is that if you have the ability to surround your signal layers with ground and power planes, that would be a really nice ideal situation. Sometimes you don't always have that choice, but you definitely want a symmetrical stack up where your ground and power planes, however they're positioned within the stack up, are evenly distributed. And in order to minimize EMC and crosstalk, you want to follow some rules on the dielectric spacing, which are listed here. Let's see. I'm going to switch to a demo if that's okay for Vandana to do a stack up demo, and I'll come back to my slides at that point.
Hi everyone. Our PCB Stackup Designer tool provides manufacturable and cost-optimized stackups and also includes an impedance calculator. The tool allows you to change the signal pin combination and the copper weights in the generated stackup. It also allows you to download the stackup data in IPC standard 2581. First, you need to enter the board information here. Let's go with the project name, a revision number, the PCB size, and use the drop down here to choose the PCB thickness. Same for the material. You can use this material selector compare guide to view the data sheets of various materials and compare their attributes. Once you have the board information, you need to choose one of the listed design approaches in the stack up design section here. You can choose the first option if you know the number of layers required in your design, or if you have a complex BGA that dictates the number of signal plane layers in your board, then choose the second option. Let's go with option 1 for now and choose a layer count. Choose a signal plane layer combination and click on Run Stackup Designer. You will be presented with the Sierra Circuit's recommended stackups. This table gives the stackup information like the signal plane layers, total number of layers, standard or HDI, sequential lamination, technology level, and cost index. You can click on this report button here to view the final stackup that resembles your final build-up. Once you click the button here on the report page, you can view the attributes without going back to the previous page. And if you do any changes to your board properties here, then you have make sure that you click on this generate custom stackup button so that you update it. Scrolling down further, you can see a detailed construction of the chosen stackup. And on it provides the information on the material, layer type, copper percentage, etc. Here you can also change the layer type. For example, from plain, I can make it to signal or mixed, and the copper percentage is also automatically adjusted here. Next, you can scroll down and we have the built-in impedance calculator. This will allow you to add controlled impedance and compute the trace width and trace spacing for a target impedance. To add the impedance, you click on this plus sign here, and you have a fresh line added to the impedance table. Here, you can add the signal layer using the drop-down, the target impedance, model type. Let's go with single-ended. Select a reference layer. The transmission line model is also automatically selected here, and you can click on calculate. The trace width and the calculated impedances are displayed over here, and you click on view, and the impedance calculator will be opened where you can see the detailed calculations, and you can also maybe see the other parameters and go ahead with that. You can add in more impedance rows over here and calculate the impedances. Further down, you have the technology parameters and the cost index. Click on this save button and it will generate a ID that allows you to access the stackup in the next login session. And if you click on export to IPC 2581, the stackup data is imported in a .xml file, which can be implemented to any ECAD tool, which supports IPC 2581. Thank you so much.
Thanks, Vandana. Let me share my screen again. Can you guys see my screen okay?
Yes.
Okay, great. So here's some design strategies you can use to achieve good controlled impedance. You definitely want to route with certain techniques. You want to keep your trace widths consistent. Spacing along the signal transmission path should also be consistent. Thicker copper usually lowers the impedance. You want to use a daisy chain configuration instead of a multi-drop branches. Multi-drop branches can cause signal reflections and other interferences. And then when routing your signals over two reference planes, if you must do that, you probably should not do that, but if you must, then you can incorporate some stitching capacitors to achieve a continuous return path. And a couple more suggestions here, but basically, when routing control impedance traces, you need to take into account all these things and not just, let the auto router run. So you have to be aware of these things. So how do we help determine that impedance is good? How do we ensure that we're building to spec? So one of the biggest ways we do that is we control our manufacturing processes. So there's always a test on the etching machines, prior to running that shift, to make sure that the etching machines are running within, proper parameters. We also, have testing coupons on our panels as we're building, so that we know that at the end of the build, that not only did we etch the traces correctly, that we laminated correctly, and the predicted press out thickness was also correct, and so therefore we're going to achieve the desired impedance. So there's lots of checks in place specifically for verifying impedance, that we've done a good job on impedance. With that, another quick impedance demo.
So here we have Sierra Circuit's impedance calculator, which uses the 2D numerical solution of Maxwell's equation for PCB transmission lines and renders fairly accurate results suitable for use in circuit board manufacturing and engineering analysis. The impedance calculator tool supports 82 impedance models with multiple geometries such as the coated, uncoated, embedded microstrip, and the strip line. And with each specific model, you can choose single-ended differential pair coplanar, with or without ground, etc. This tool is also integrated with the signal loss, crosstalk, and S parameter calculators. Let us start with a coated microstrip and a differential pair, for example, and click on open. Usually the simple and the complex model both will be displayed.
Thank you.
Yeah, so sorry about that.
Oh, yeah, no
Yeah.
problem. Do you have more to
So
demo?
here, yeah. So
Okay.
here we can choose the desired units for the calculations. We'll take mils only for now and enter the dielectric information. Let's go with 3.348 mils here, a dielectric constant of 3.63, coated height H1C as 1.5. Coating height H2C has a default value of 0.5, but you can always change it if you wish to do so. Then we have H3C and the coating dielectric constant ER22. If you want to calculate the trace width, we enter the delta W here. Delta W is the difference between the top of the trace and the bottom of the trace. And you can click on this help button, which will display a table that suggests the delta W values based on the starting copper weight. So you can use it as a reference. So let me enter 0.5 mils for now. Enter trace thickness of about 1.45 mils and a trace separation of maybe 7 mils. Enter target differential impedance. Let's go with 100 ohms for now and click on calculate W. The trace width and the other parameters like the uncoated differential impedance, coupling coefficient, etc. will be calculated and displayed. Then we can move on to the signal loss calculator for the same chosen model and enter a dissipation factor. Let's go with 0.024 for now. A frequency of 10 gigahertz. Surface roughness of 6 microns. That is the standard roughness for a foil, and enter the length too. Click on calculate loss, and the signal loss output in the odd and the even mode will be calculated and displayed. Similarly, we have the S parameter and the crosstalk calculators for the same chosen model, and you can use all of those. Thank you.
Thanks, Vandana. Okay, I have one more slide and then we'll pass it over. So here, we just wanted to summarize some key DFM guidelines to ensure EMC. So as mentioned before, you want to ensure sufficient spacing between your signal, power, and ground planes when you create your stack up. And our stack up tool will definitely help you do that and follow the best practices. When you're routing your traces, if you can have more rounded track corners, that's better. You definitely also want to avoid features that could produce slivers. When we're manufacturing boards, slivers can become an issue in the manufacturing. Let's say it's a sliver of resist material, then it could easily peel off during manufacturing and then deposit itself other places, which would then cause failures and yield issues. So slivers are important for manufacturing as well, to avoid slivers. Now, spacing towards the edge of the board, 7 to 10 mils is good. I think we can do better because of the routing tolerance of our machines. However, you want to avert, any kind of radiation leakage as well. So there are some things to consider aside from the capability of the machines. And then ground pours, properly use ground pours in building and designing your PCBs. It does help with the manufacturing of PCBs. Having more copper pour helps with adhesion in lamination. It helps with controlling your etching. But don't do things like creating isolated ground islands, which can definitely have unintended effects and generate EMI. So when routing your RF traces, you want to have spacing between the RF trace and the ground pour. A rule of thumb is 1.5 to 2 times the trace width, and this can help reduce the coupling. So these are some pointers. We have a lot of resources on our website, and today we have expert advice. But if you want to do more research and educate yourself on these topics, we have these wonderful blogs and design guides for you. With that, I'll pass it over.
Great, thank you very much, Amit. Thank you very much, Vandana, for the presentation and the demos. It was very, very interesting. So to move forward, I will share my screen. Let me share this. So can you see my screen right now?
Yes.
Can you see this? Great. Can you see the slides? So today, what we're going to go through. So we're going to review some bad, good, and better techniques for PCB layout and PCB. So some topics were already covered by Amit, and we will see how to improve gradually the EMC quality of the designs. Also, we will see how to prepare a cost-optimal EMC test campaign, or what's the best approach to start preparing an EMC test campaign. And the last part will be a demo for platform, and we will give a space and time for questions and answers. So I have seen that there are a few questions already in the Q&A, so please write everything you have in your mind so we can answer them at the end of the session. So let's start with the techniques for PCB layout for EMC. So there are a few things, there are a few topics that every designer needs to have in mind. So one of the first problematic aspects of PCB layout is the distance, is the space. So we are designing more and more dense electronics, and we need to have some space between components and traces. So one of the most common challenges, and when it comes to high speed PCBs, is that we don't have all the space we would love to have. So that means that in the end, we end up having high speed signals very close to each other. And then this fast edges, this very short rise time and downtime, in the end, they provoke crosstalk. So they degrade the signal integrity of the PCB, and it's a big problem. So one way to do it, and in the good situation or in the luxury situation where you have a space, the best and easy moment, or the best and easy solution, is to increase the space between traces. And in the even more luxury situation, is the best solution will be to increase the space, but also to fill the spaces with ground plane. So it's also a cheap way to add shielding, so you don't need to add any extra component, but it comes with the price of the space. Also, so when it comes to EMC, one concept that we talk a lot about is the return path, and we know that we always need to keep the return path. So here we can see a chip, an integrated circuit that has been installed in a 2-layer PCB, and that we can see that there are holes in the planes that signals. So it's not that easy to go from one part of the chip to other one. So that means the return path is very, very long, which in the end it creates ground bouncing and radiated emissions, among other problems. So always, whenever you have a component, an integrated circuit, or any other kind of component, always guarantee that you have a very short return path. And by short, we mean very low impedance. So one solution, which is moving from, well, in this case, 2 layers to 4 layers, that today makes totally sense. It doesn't make so much sense to say no to a 4-layer PCB because of the price. And so please add solid ground planes, and don't finish the job just pushing the button or filling the ground plates and then sending the files for manufacturing. Check the files, check the routing, and also look for bottlenecks. Guarantee that all the pins, all the input-output pins, and all the power pins, they have a short return path. Also connected to this topic, so we have a different way of saying keep the return path short. Also is make the connection to ground short. So before we were talking about ICs and ground planes, here we talk about capacitors. So it's a very common situation to have the coupling capacitors where they are powering an IC through the so they're not powering, but they are decoupling the power pin of an IC. So if they need to be very close to the IC, so that they are efficient, but also the connection to the ground or to the return signal or plane, that needs to be very, very short. So in the first pictures, we have that the capacitor has some connections to ground, but we see that vias can be very long, so they have to go all this distance. And it is any copper, no matter what kind of copper, if it's a ground plane or a power plane or a trace, every copper has impedance, and it has some parasitic elements that we always need to reduce as much as possible. So in the case of the coupling capacitors, we do it by adding some vias. So in the second picture, we see that it has a via, and the coupling capacitor has its own via, so it's a better situation. But still, I think that we can go one step further. And the best situation when we have space and when we can afford that from the manufacturing point of view is to add more via. So in this way, the total inductance is divided, and the decoupling capacitor works as a real capacitor. Whoops, here. sorry, I had some issues with the presentation. Let's go here. Yeah. So related to vias, so vias are very useful to reduce the total impedance, and so it's very common, mainly when we are starting or to do a new design, and or when we're starting in the design, the design activities is to fill all the PCB with planes, and then say, yeah, I already added ground planes, so I know that my PCB is going to behave well on EMC. Well, it's not that true, because you need to be sure that you connect the top layer with the bottom layer with the inner layers, and you need to guarantee that these connections have a very, very low impedance. So in the first image, we see that there is a top plane, there is a bottom plane, but there are no vias. So where are they? And so then we can add some vias, but still the distance between consecutive vias is relatively high. So of course, this definition of high and low will depend on the application, if it's high frequency or radio frequency, or low or a power PCB. But if we are talking about the high speed PCBs, we need to guarantee so we need to be careful and to add a lot of vias, and that the distance between them is not very, very high. So a good rule of thumb, and it's really a general rule, is to add vias that are separated between 3 to 5 millimeters. And the last but not least, so we have a common challenge is that today we don't have systems that are made just with one PCB. So normally we have one PCB, 2, 3, whatever. And also that these PCBs, these systems are not made just to be alone. So they are being manipulated by humans, they are being manipulated by machines. So that means that they need to be protected against us as humans, because we are very good charge generators. So we are very good electrostatic generators when we work in the office. And that means that the electronics we design, they need to be protected. So we usually, one technique that is the very first step is to every component, so every connector, every interface from the PCB to the external parts, we add protection elements. So these protection elements can be different types depending on the type of disturbance that we plan for, but we always add protection and any kind of protection circuit. And these components need to be very, very close to the connectors, so that we ensure that the distance between the interference coming from the connector to the protection element is very short. But also, same as with the coupling capacitors, this connection, so the connection from the components to the return point, normally ground or the mechanical case, needs to be very, very short. And we do that again by placing vias very close to the pin. And again, to make it very, very efficient, that inductance, that parasitic connection needs to be as low as possible. And in protection elements, this is very important. So 1 via is good, 3 are better. So that we guarantee a very, very, very low inductance. So to summarize, those are the most common problems on EMC at the design state, let's say. For advanced designers, those are so they incorporate it in their automated way of work, automated way of thinking. But it's very, very good to remind all of them. So to be sure that, well, we are focused on the most advanced topics, we don't forget about these other topics. So those are the most common issues. And also, apart from being common, they are relatively or very easy to fix at the design phase. And it's way more difficult to fix while the PCB has been already designed. So then the second part, since we are talking about EMC, we are going to talk about how to prepare a cost-optimal EMC test campaign. So EMC, it's not only for the EMC people of the EMC engineers, it's also for the designers, because you as designer need to design a system that is EMC compliant. So let's see how your role as designer can have a significant impact in the EMC results. So we have two situations. So it's the old way of thinking about EMC versus the new way of thinking about EMC. So the old way, the classical that we have been all educated there, is that we don't think on EMC, or we don't think about EMC until we have the board working or the system is working. So priority is the highest priority is to have a functional board there, and we will care about EMC at a later stage. So the problem there is that this can provoke unnecessary redesigns. I say unnecessary because if we think about these problems at the beginning, the space and time for adding these extra components like EMC filters, protections, or the coupling capacitors at the beginning it's way more easy than doing it at the EMC chamber or while you are or where your production is already ongoing. So the new way is that we design for EMC. We start thinking about EMC at the design phase when we are still at our CAD tool. Also, so the second common thought is, okay, we know that EMC has been always hard, so there is no reason to do it otherwise. So we have been always suffering with EMC, so it's going to be like that. So we wait until the end, and then we expect the suffering, and then we go through it. The problem with this or the impact is that this gives us a little space and time to react. There is a lot of stress. There is a lot of emergency calls to the EMC labs, to the PCB manufacturing plants. Please manufacture this for tomorrow because the EMC lab has no slot before the next 2 months. So in the end, you are more than designing or manufacturing a reliable system, you are firefighting. So there is an alternative way, which is reallocating money for the design for EMC. So instead of putting all the money on the end, that you share the investments through all the design lifecycle. And the third one is that we send so it's more related to responsibility, is we send the prototype and the laboratory takes care of everything, so they do everything. And then this provokes a lot of surprises because the laboratory in the end does not have all the capabilities to support us. So this provokes a gap in responsibility. So we end up in a situation on, okay, who is going to do that? Who can take care of that? So that gap provokes delays and confusion. So if we plan for EMC at the beginning, that means that we know where we are going to spend our resources. So the old way of thinking brings a lot of stress, while the new way is more calm and relaxed. Okay, so this was the very, very generic or the introduction. And now if we go to a more practical oriented solution, is how we're going to prepare an EMC test campaign. Okay, so you are a designer, you want to prepare an EMC test campaign, how you do that. So first of all, at this moment, it's when it comes to the time to cut the just in case options. And what I mean for that is, okay, we're going to see is there are two phases. So it's the laboratory request. When you send all the information, you are going to have requests from the lab, and then you are going to make yourself a few questions. And we're going to see why. So first, if you have designed a system with a lot of ports, just in case, because maybe you have an auxiliary programming port or an auxiliary port because maybe a customer requests an extra feature, it's the moment to ask, hey, it's something that I really need, or I can remove it for today. So then keep it as low as possible. So you will reduce the number of tests. That means that you will reduce the number of time you spend in the lab, and you will reduce the money you spend in the lab. Also, you will not certify just a PCB, you will certify a system. A system has cables, and cables have a specific length. So check if all the cables need to be that long, because it matters during the EMC certification or during the EMC test, because longer cables need to go, since they can create or they can generate undesired emissions. So you will need to pass more tests over long cables. So less cables, less tests, less problems, reduce the cables as much as possible. Same with the voltage levels. If you prepare a system to work on a wide range of voltage, you might need to go through safety tests, which in the end it increases the amount of tests that you need to make, the complexity, the documentation. So if you don't need to go, so you can keep the voltage levels low, or the input output voltage at your system, and you can keep it simple. So do it, because you will reduce the amount of work you need to do there. And the same with operation modes. If you are designing a system that can work in 10 different situations, but your applications for the first 3 years is going to be a much more specific one. So limit the operation modes to the most simple ones. So don't try to design the one for everything, because then you will spend days and days and even weeks in the lab. So those are the parameters and things that you need to check while being a hardware designer that will have a huge impact on the EMC budget in money, in time, and energy. So then now to end up here, I'm going to show a demo of the Denpaflux platform, and then we will go to the Q&A questions, the Q&A phase. 1 second, let me check. Share my screen now. Great. Can you see my screen? The Denpaflux platform.
Yeah, yes, we can.
Great, thank you. So this is a Denpaflux platform. So here we are very focused on EMC, as you can imagine. And what we do is we provide EMC assessment at the very early stage of your process. So once you create an account, that you can create one already today, so you don't need to do anything else. You can come to our website and create an account. You can see some of the projects we have already there. So once you have it and once you start working with the platform, you will have a view of the projects, and we can go through them. So for example, let's start with this one. So the images you have seen through the presentations come from this board. It's a small board, MMS-P430, which is an industrial automation board with a Wi-Fi module. And this has been designed to be sold in the European Union. So we need to go to the EMC lab, and it's an IoT board. What we can see here is the historic of the EMC recommendation report. So since the very beginning, so the board has been, the first board has been submitted on the 21st of June. So we can see one of the recommendation reports. So this, you can upload your boards while you are designing. So that means that you don't need to wait until the end of your design process to have an assessment of your EMC. So also this is very useful when you are a designer and you can test with different options. You can upload them, have feedback, and then keep designing. So here you have an interactive viewer where you can see all the EMC problems or all the potential problems you can have in your board. And here at the right side, you have the detections and recommendations. So this is the EMC recommendation report. Those are the list of potential problems explaining why this is a problem, how to fix it, and why the fix is going to be useful for you. This is a PCB viewer, so that means that we can select which kind of layers we can visualize, and also we can zoom in, out, so you can navigate through this as in a regular PCB viewer. What is very interesting is that we follow an iterative approach, so that we don't want you to come just once and then you go to the lab and never hear back from us. We want you to go to all the design states, all design parts while you advance and reduce the risk on the EMC assessment. So the idea is that you start with so at the very beginning, where you can have a lot of issues. Then the second one, you come and you have less issues, and then in later iterations. So the idea is that you come and you have green light and you're ready to go to the lab. And just one more, and then we can go to the Q&A. So here I have shown a PCB, but it's true that we're not working just with PCBs. We're working with any kind of file or any kind of electronic file. So it can be PCB, but also it can be a schematic. It can be mechanics. So that in the end, what you will have is an EMC assessment of your whole system. So the important thing is that we follow, so the reports are very short, in the sense that they don't have 200 recommendations, 300 recommendations, and then it's complicated to read them or to go through them. So they're very short, so that you focus on the most important things, and then you fix those problems, and then you come back again and in very, very short time. So that in this way, at the end of all the iterations, you are sure that you have the different parts of the PCB. So you can start designing the communication part and then upload it to the platform. You can keep working on the microcontroller area and then upload it. And in this way, we can go with you through all the design steps. And with this, we have 15 minutes for questions and answers. So then I will stop sharing and let's go.
Before we start the Q&A, thank you so much for the presentation. I'm going to launch a last question, which should pop up on your screen now. So it would be very helpful if you could tell us what topics you would like us to cover during the next webinar. Thank you so much. I mean, do you have any suggestions of topics we could do? So it can be EMC, signal integrity, GFM, EMI, anything you want.
Yeah, I was thinking that also, Ignacio, we can discuss after a few things.
Sure, my pleasure.
Okay, I'm going to leave the poll on, so you can take your time to reply and post suggestions. But in the meantime, I guess we can also get started with the Q&A. So I see we already have one question.
Yes, so you got one question that has been answered. The other one is for us. Is Denpaflux an automated process or a manual review? And what are the costs? So this is something that we're not hiding at all, so we're very transparent. Today, it's a mix. So we have what we name a human-machine approach. So that means that we have a set of internal tools that are not very good to be shown directly to customers. So that means that they generate an output that is always reviewed by the human, so that we filter the noise, and then we generate this very important report where you have the most important problems to focus on. Also, what I have not shown, so I have shown the platform with all the reviews or with the packages. we have always an EMC expert assigned to your project. So that means that after the reports, you have the chance to have EMC calls, what we name. So those are sessions where you can spend time with your EMC expert talking about the reports, talking about any other EMC session or even EMC questions you might have. Related to the cost, we have different packages, depending on the size of the project, depending on the iterations, and not iterations, but depending on the number of PCBs, project, and time, the price varies. So my suggestion is that you send us directly an email, and then we can discuss the project. So Jeremy, I saw that there is a credit system. What are the different options? Do different options allow you to test different standards, or what is the difference? No, it's not related to standards. So it's the different credits is in terms of reports. So in the end, not every company works with the same number of complexity levels. So the credits, what the credits are the EMC reports you request.
Okay, thank you. Do we have any other questions? Just so you know, we also have our manager of R&D, Steve Carney, in the call with us. So if you have any questions regarding board fabrication, just you can ask.
Also, Lucy, correct me if I'm wrong, everybody will get the slides and the material, right?
Yes, I will send them this afternoon. Oh, we have another question.
So for each board review, if revision is a cost, a credit per project or per review? It's so it depends on the package. So, let me open, since I'm seeing many questions related to packages. See, I can share here. Yes. So let me share my screen very fast. Great. So today what we have are 3 packages. So one is the entry, the pro, and the ultimate. So the entry is to test our services and also for a small project. So it's one project. It's 2 iterations. So that means that you have access to 2 EMC recommendation reports. And also it's 2 EMC expert calls. So as I said, it's 1 or 2 in this case, 2 technical sessions with your EMC expert where you can discuss the recommendation report or the design that you're working on. So imagine that you're planning a new project and you want to design, you don't know which stack up you can use. So we can have one session talking about different stack ups and the one that can be the most suitable for your project, also considering other restriction points you can have like cost or mechanics. The pro package with when you need to work on one project, and also that you know that you are going through, or you need to have good quality, good EMC quality. So that means that you start your project and you start uploading your files since the beginning until the end, and you can have unlimited iterations. So that means that you can submit your files whenever you want, how many you want, and you will have 5 EMCs per call, the same way as before, but in this case 5, and this is one for 12 months. And then the ultimate package, which is same but for 3 projects, and it's really unlimited, but those three projects. And what changed is the number also of EMC expert calls.
Okay, we have more questions.
Amit, do you want to go for some of them?
No, I'm fine. I just wanted a quick discussion with you after the webinar. I'm not
Okay.
sure how to do
Yep.
that.
Next question, how important rounded corners at what high frequencies should be concerned? So this is like the magic question to trigger all the EMC community. The fast answer is so not really important. So it has been proved that they are not really like that. The non-rounded corners or the 45 degrees corners are not creating a huge impact on EMC on reflections. So unless you are working in really high frequencies, so that you are designing really radio frequency circuits or antennas or things that are specific applications, you don't need really to be concerned about that. If a PCB mounted inside a metal enclosure has some EMC leakage, what methods to seal it? Can I apply EMI tape to the board, or will it be better to seal the enclosure? Okay, so EMC leakage. So this is a critical point, and it's not that easy to debug. And I will go for as I mentioned before, for an iterative approach. So not trying to solve everything with EMI tape or copper tape, the classical copper tape that you have in the EMC lab, but really to try to figure out where the problems come from. So first, check if the mechanic enclosure is as good as you want, so that the metal enclosure is very a good conductor, but not only in DC, which is the classical check that everybody does, but with the multimeter. Be sure that that in high frequency is not going to, it does not have a lot of variation. It's very common that mechanical enclosures have some kind of puncture or some kind of galvanization. Check for that, because those are very bad for EMC, because they change the impedance. So that will be the first thing I will check. Also the connection from the PCB to the mechanical case. So for example, if you are using screws, to be sure that the screws are touching so that the surface contact is very good, and that there are no mechanical elements that are good for mechanics but not that good for EMC. And if none of that works, what you can do is use EMI gaskets. So those are specific mechanical components that are fit between the mechanical cases, and those help to contain the interference inside the case, or contain the radiations. So those are three generic advices. Depends a lot on from system to system, but I will go for these three elements, three steps.
Okay, thank you very much. Well, it seems like we no longer have any questions. So I guess we can end the webinar. Thank you very much. Oh, no, one last question.
Okay. Question from Marco. Hello, Marco. Nice to see you here. So how do you take into account the effect of housing on the PCB EMC performance as power filters? That's a good that's a good question, and challenging for power applications. So I struggle to define how you take into account. The first approach is, okay, try to keep all the switching sensitive elements from other areas. So keeping chokes, inductance. So keeping chokes far from mechanics, inductance, and capacitance, so from all other mechanical elements, because there you risk of having capacitive coupling there. So how you can distinguish from comes from the PCB and what comes from the implementation? An easy test, and I'm going to say it's relatively easy test, is that you test the radiation, or that you measure the radiated emissions, conducted emissions in the lab without mechanical case, and the other one, and you make another test with the mechanical case, and then you can see more or less what are the differences. Of course, it depends a lot on the system, but that will be one test that I will do to discard or to see what is the impact of the mechanics.